Hello everybody. So just wanted to go through one of these homework problems that you guys did just to give you a little bit of a background and just go over how to solve these problems and then work through the MATLAB coding a little bit just from start to finish so we can make sure that everybody's on the same page when it comes to solving these types of problems. So we're just going to go over 8-3 and just go through a couple of these parts right here and try to figure out how to solve this with MATLAB. So the first one is just it's a couple of reactions going back and forth. You have a desirable product and an undesirable product taking place in a batch reactor. Okay. We have this additional information, which are just going to be the constants. And then we've got the rate laws, which are given. So let's just solve this now. So it says to plot and analyze the conversion and concentrations of A, D, and U as a function of time. When would you stop the reaction to maximize the concentration of D? Describe what you find. So the first thing that we're going to want to do is you can start with just a simple N equals out, a mole balance, right? So you can say in minus out plus generation equals your accumulation term. So if we have a batch reactor, there's initially just C naught, and then over time we're going to have U and D. So we just have a batch reactor, which means that we're not having anything in or out. So these are both going to go to 0. So we'll just have a generation term. In this case, it's going to be the rate of A, being your generated or consumed, is going to be equal to the accumulation of A as a function of time. So it's dCA dt. What you can do is you can check the units on this as well to make sure that everything that you have on here is correct. So units of R is going to be in moles per decimeters cubic or whatever, times some time term, we'll just say minutes in this case. And then we know that concentration, or concentration term, ET term, concentration we know is moles per decimeters cubic or something else, and then per time, so it's going to be times a 1/minute term, so we know we have the same. I'm just doing this because there could be a situation where you're trying to do it in terms of just something other than dCdA, or it's something other than R. So there could be a situation where you have R times T. That would be when you're just looking at, something like dCA dV, I think. Okay, so now that we know that we have the correct units, we can then just keep going with this problem. Okay, so that's going to be our A balance. And then we can do a mole balance for just the other ones. Okay, so that's going to be our mole balance for each one of these, because nothing's coming in and out, so the in and out terms are going to be 0. However, it's a batch reactor, and we're going to have an accumulation over time over this reaction. So the next step is going to then be figuring out the rate law. So we can determine our rate law as a function of R. So we know here that if we just write out the equations again, A is going back and forth between D, but A is also going back and forth between U. You should be able to figure out how to get these rate law expressions, but in this one they just give it to you. One thing that I want to highlight is right here. These are the equilibrium reaction rate constants, so they're not the same. These two are not the same Ks. These are very different Ks. This is the K for the forward reaction, this K2 and this K1, whereas the K1A and the K2A are your equilibrium coefficients. So what we now need to do is just figure out what is these rate of reactions for each one right here. And to do that, let's start with A. So if we're looking at the rate of reaction of A, we notice that A is being consumed or produced in each one of these reactions, so that we then need to just add them together and say that the reaction rate of A is just equal to the reaction rate from the first reaction plus the reaction rate of the second reaction. I know there's negatives here. You can just distribute these negatives in and it'll give you the same. That's usually how I like to do that, but you can just do whatever method is good for you. Either one's going to give you the same answer. So we just say that the total rate of reaction of A is then going to be equal to negative K1 times concentration of A minus CD over K1A. So that's just this first one, and then plus, so it's going to turn into a minus, or R2, our K2 times our CA minus CU over K2A. So our A then is just equal to, so that's just what our reaction rate is, and we can then just take this and plug it into there. Okay. Next, we need to figure out what is our rate of reaction of D now. So our D is not equal to, our rate of reaction of D is not equal to our rate of reaction of A, or the negative rate of reaction of A, because the reaction of A is present in both reactions. So it would be incorrect to say that your reaction rate of D is equal to negative reaction rate of A. That's not correct. What is correct is to say that your reaction rate of D is equal to your negative reaction rate of 1A, of just this first reaction right here. So if we can do that and plug it in, we'll say that our negative reaction rate of D is just equal to positive now K1 CA minus CD over K1A. Now this is true, and we can then take this and plug it into there. And then similarly for C, we can say that our reaction rate of C is equal to negative R2A, which is equal to K2 CA minus CU over K2A. Okay, so now if we just rewrite these differential equations in one set, we can then plug those into MATLAB. So these will then transform into the following. Okay, so this is pretty much going to be the main equations that we're going to plug into our MATLAB code. If you get to this point, you will determine that you can't really do this by hand. It's going to be really tedious. It's going to be really hard to do because you can't take the derivative of CA here because we have a CD term here and a CU term in here, which are all interdependent on each other. So it's something that's going to be not realistic, or something that we're just not going to want to do in this class. That's just a bunch of math. And so what we want to do at this point is we would just want to plug it into any type of solver, any type of program. In this case, I'm going to plug it into MATLAB and have it do all the heavy lifting for us. Lastly, we want to make sure that we figure out what is concentration, or I'm sorry, what is conversion going to be equal to. And that's just going to be conversion is going to be equal to 1 minus just that right there. So these are going to be the main equations. These four are going to be the main equations that we're going to be plugging into MATLAB. Okay, so what I just did here is pulled up MATLAB through the VLab that you should all be familiar with accessing. If not, if you have any issues, please feel free to reach out to me. But once you reach this main screen in MATLAB, what you're going to want to do is just create a new script. And now right here in this area is we're going to be running the MATLAB code. So the first thing that you're going to want to do is you're going to want to introduce the CHE3400. It's just a way to solve ordinary differential equations. It's a built-in program that's in MATLAB, and in order to do that, all you would do is just say, let's get a couple of spots here. So what the percent sign does is it just says that anything that's after the percent sign is not going to be used inside the code. It's just used for doing text. So in order to do this, you would do this t comma y. That's just going to be what it is that this is what two variables your differential equation is going to be a function of. So the first one is going to be like a typical points, x, y. So it would be time, and in this case it's going to be y, which is going to be our concentration, which will get solved in later. So just say that is equal to ODE45. You can see right here, it's kind of already telling you what it should be. T-span, you can just click into those and get a little bit more in-depth if you want to. It can give you a lot of information too. So that's what's going to be your first line. So you're just saying that you have your differential equations that are going to go through a span of t, which is time, and then you're going to have y of 0. So the next thing that you're going to want to do, probably, is you're going to want to take these equations that we did previously and just plug them in. So I'm going to do that right now. Okay, so you can see that right here, what I just did was I just called out the function. Say there's a function dy dt, which is going to be equal from the set of my ordinary differential equations, which is going to be functions of t and y. And so what I did here was I just said, this right here is something that's necessary, just calling the zeros. So here are the actual differential equations. You can see that d1, dy dt is my first one, dy dt the second one, and then dy dt is my third differential equation. And these are just coming straight from what I showed you all previously on the PDF file. So what you might be tempted to do is just click run and see what happens. And you see we get a couple of errors. It doesn't know what t-span is. It's saying that there's an error in this line. So what that first error is doing is that you're not giving it the span of time to run. So we can fix that by adding the following code. So what I did here is I just said, okay, I'm going to let my t-span range from, you can just say to 100, from 0 to 100 minutes. Now let's see if it runs. So again, it's giving us the same error that it doesn't recognize it. That's because we are not telling what it is before we are entering the t-span. So we just need to take this and put it above, and then that one error should be resolved. That one is resolved, but we still have an error with y not. It doesn't know what this is. So we have to fix what that is. You can see that there's going to be a lot of just, you can do a really hard trudging through it and trying to figure out what the issue is. I'm going to kind of skip a couple of steps just for the sake of time and just kind of show you what the general format should be. But right here, the main issue is just that we don't have what our y not, what our y0 is equal to. And to fix that, we can just say, well, we're going to let y equal to 1, 0, 0. This is our placeholder for CA, this is our placeholder for CD, and this is our placeholder for CU. So this is just a vector that's going to be, it's a matrix that's going to have a set of vectors. Yeah, you should be familiar with that. So then if we try to run it again, now we're getting all kinds of errors. A lot more errors actually this time. It doesn't recognize what K1 is. It's because we don't know it doesn't know what all these are. So K1, we know all these constants are easy enough to fix. So we can just fix that right now. So we can just do that like this. We can just define our constants and say, here's our K1, K2, K1A, and K2A. However, this still is not going to run because it's going to be trying to figure out what is our CA, what is our CU, CD. So we have to tell MATLAB that our Y's in each one of these positions in the matrix is going to be assigned a specific value that we say CA, CD, and CU. So to do that, we can just do that right here. We call that essentially unpacking the variables. So here we'll say we'll unpack the variables. That's just saying that CA is equal to Y1. What that's saying is that's going to be equal to our first row in the Y vector, or in the Y matrices that we have right here. CD then is just going to be equal to our second row in the matrix, and then finally our CU is going to be equal to the third row. Okay, now that we have that, let's see if it's going to run this code. Okay, so it ran the code, but nothing really happened. Looks like we have T might be unused. Just ignore that one. So we press run, but nothing really happened. It's because we haven't told it to do anything yet. What we can see is we can click on this right here, and it'll give you the values of what each of these Y's are. So we're saying this is our concentration of A right here. You can see that it's starting at 1 and then going and increasing with time. You can see right here, this is our concentration of D starting at 0 and getting larger. But the only reason why it's not giving us a graph is because we haven't told it to give us a graph yet. So to do that, you have to use the following functions that I will show you right now. Okay, so right here, what I'm doing is I'm telling it to run exactly what I told you all before, explaining the t-span, the space in which we're going to be performing the differential calculation, and then we're going to have the actual differentials worked in right here in this little section where we're going from function. One thing that I want to note is that we have this function to define what we're going to be doing as far as the differential equations, and then it's important to have the end right here. So what I did was just put how to generate the plots. So that's just a matter of just saying figure, and then just having the plots. So you want to plot t versus y colon. What this is saying is you're plotting all of the values of y. So the colon is just saying that you want to track all of them, and this 1 means that we're taking the first position. So this would essentially be CA1 or CA. So this is just saying that we want to take all the points. That's what the colon is for. And this is saying that we're taking the first y component in the vector in the matrix, which is again CA. You can see here that we just keep saying that we're holding on, saying that we want to hold on these following plots onto the same figure. So what this is saying is we now want to plot CD and CU. So it's exactly the same. We're keeping and we're plotting all of the data points that we're calculating, but we're taking the second row in the matrix that we just described above, right over here, right here. So what we're doing is we're now grabbing our desirable product. So we have that, and that's to actually generate the figures. What you can do here is you can add labels and legends. So you can say add our X label, it's just adding X label, and then you put these little single quotation marks will generate whatever it is that you want it to say. I can say time in minutes, and then Y label, we can just say here, you just say concentration. Title, we can say, what do we say for title? I don't know. Concentration versus time, sure. Then we're going to show the legend, and we can have grids if we want to, or we can take the grids off. So now that we have this here, let's click run, and we get an error. The only thing this error is telling you that we have to put it in front of the MyOD. So function definitions in a script must appear at the end of a file. Move all statements after to before. Okay, so it has to be before the first local function definition. So that's easy enough. All we're doing is we're taking this, getting out of it. So here's the first function definition, right? So what we're going to do is we're going to plug it right into here, and then see what we get now. It's thinking. You can tell that it's currently working because it has this pause symbol and as well as stop. So there we go. We have a graph now. You can see we have time, that's in minutes. The title is right here, concentration versus time. We have concentration over here, and it's giving us the color scheme that we're looking for. So red, green, and blue, something that I think I skipped over, is right here. So you can just say plot, time, concentration, and this is going to be the color of the line. So you can say that you want this one to be black or whatever, and it'll just change the color of that. Or blue, I'm sorry. If you're not really sure what the color codes are, you can just Google them. You can use any color you want. I think yellow might be one. And there you go. So here's the graph that we're looking at. The only thing that we're missing, however, is we're missing the conversion. Remember? So we have to now add our conversion calculation. So to do that, we can do it right after the graphs. Okay, so this is just going to be the code. This is pretty straightforward. You're just saying conversion is equal to 1 minus, so what you would be tempted to do is you might want to say that this is just CA, right? CA over CA naught, which in our case CA naught is just this right here. However, I'll show you right now why that's going to be an issue. The reason why also we need to then bring up another plot, we need to tell it to plot a separate plot for our conversion, so we'll do that now. So here we go, right? We're just going to call another figure. We're going to say plot T, plot X. We're going to use a line of black, and we're going to call it the conversion of XA. We're going to call it XT, and then we're going to just do the labels and everything, and we're going to give it a title. So let's see what it does now. Oh, so now it's not really telling us anything, except for we have an error down here that's saying that we have an unknown variable, unrecognized function or variable C of A. So this is not able to perform this calculation because at this point it doesn't know what C of A is. We didn't introduce C of A anywhere. So what we can do, so here is our calculation for conversion, right? And at this point we haven't introduced C of A. So let's see if we can take this inside the function and see if that changes things. So what I did here is we're now putting it inside of the function and trying to see if it works that way. And again, we have a figure 2 now popping up. However, it's not giving us the graph we're desiring. It's saying that there's an error, unrecognizable variable x. So it's not an issue that it's being inside the function. The issue is this. So the issue is we need to put it here. The issue is that what we're going to give it is, first of all, when we pull it out here, it's only going to give us x equals 1 minus c of our final concentration if we were to leave it within the function. So what we want it to do is we want to plot as it stores all of the values. So since we're out here and we had just defined since we had just defined that everything's going to be stored as y's, we want conversion, which, right here we know that it's CA, but we know that CA is right here within the first vector, vector of our matrix C. So we need it to be stored as y1. So we'll say minus y. Now see, it's asking for enter value for rows. So this is where it's asking how many rows of our x, or in this case our t, how many rows of our t do we want to store. To do that, you have to hit colon. So that says that we're going to be storing all the rows that were calculated of our first variable. So what we can say too is we can say, if we were to just give this a specific number and say we want the second one, what this would say is we are taking the second value of CA. So that would be something that's very close to 1. What the colon is telling us is that we're taking all of the values. So we're storing x as a set of values, as another array, or as another matrix of all the values of CA across all the different differentials that we've done as a function of time. So now that we've told it that we want to take all of the rows of the first column, we can then, of the matrix C, then we can say that we can safely plot it. So here, let's hit run. So there is our conversion of A, or our conversion of XA as a function of time. You can see that the other graphs are going to be hidden immediately behind it, so just move it off to the side and you should be able to see as many plots, as many figures as you want. So one thing that I do want to make sure that you are all doing going forward is labeling your plots. You must label your plots. You can't just have all kinds of plots because I wouldn't know what they are. So it's just something as simple as just saying, here's the X label, here's the Y label, here's the title of the plot. You can say conversion of A. Plot it, and that looks better. We have to be a little bit more professional now, so make sure you're taking advantage of all this stuff and making the graphs look nice and neat. Yeah, so that's as far as getting how to use MATLAB, how to put in the differential equations, and how to generate plots and figures. Okay, so now that we have our code, we can now do a little bit of messing around and see what is going on to answer these problems. So let's take a look at the concentration, as we said, over 100. The first one is asking, when would you want to maximize the concentration of D? So we see here that concentration of D, which is our green, just seems to go up, and then it sort of tails off after a little bit. So we would say that we would want to stop the reaction after, you can say after a very long period of time, but it would make more sense to say that you would want to stop sometime after 10 minutes because you don't want to keep going because there's not a significant change. So if we look here, we just change this to 20 now, or even 15. You can say that it looks like our concentration of our desirable product seems to increase, so we don't have to worry about some undesirable products coming in at some later point in time. We can just say that for answering that part of the question, when would you stop the reaction to maximize the concentration of D? Well, you find that the concentration of D just increases and the concentration of the undesirable decreases. So you can just let the reaction go for an extended period of time. If we cut off this range here and say, let's look at now what happens between 5 minutes. We would not want to cut off the reaction right here. So if we were to say, let's just say this is 1 point, it actually gives you the 0.2 if you hover over for a while. So we say at approximately 1.3 minutes, so we get equal concentrations of our desirable and our undesirable. So we would want to stay away from stopping the reaction anywhere before a minute, because we just have the concentration of the undesirable products just skyrockets immediately. So we want to make sure that we're going definitely at the bare minimum greater than 1.3. But again, like as I said, the longer you keep going, the more concentration of your desirable product and the least desirable product as you go forward in time. But it is interesting to see what is going on during short times of the reaction. So if we see here, we can get a better idea of what is happening with the kinetics. Something is happening within 1 minute of the reaction. So this is pretty cool because you can just go and check and see how is the reaction behaving as a function of time. We get an immediate drastic decrease in our concentration of A and an extremely drastic increase in our undesirable product. Again, that has to do with just the, it has to do with our reaction constants. So with our reaction rate constants. So our first reaction is for our desirable product, and we say that it is very slow. It's a K1 of 0.8, whereas our undesirable product is 90. So that shoots up really quick. That is being translated in this graph. That's what we're seeing here, is that the reaction rate coefficient is causing it to accelerate really quickly. However, as time goes on though, due to the other kinetics of the reaction, the equilibrium kinetics, you do end up getting that over time, it's favorable for the desirable product. And that has to do with our equilibrium, as I was mentioning. So higher equilibrium for this problem, specifically in the way the rate law is set up, higher equilibrium constant, even though these first initial ones are drastically different, you can notice that 10 versus 1.2, it's about an order of magnitudes greater. This is what over time ends up playing a crucial role. So this would be good for very quick, very initial conditions, whereas this is where becomes dominant over extended periods of time. It's just something to keep in mind. And then also what we can do is we can mess with that. What if we say that this is now going to be 1.2? How does that change the kinetics? So let's go over a longer period of time. Let's go with 15 again. We see now that our desirable and our undesirable just come to meet at the same point. That is because the equilibrium conversion ends up being the same. Now this is only true because of the way that it reacted, because of the way that it came out, that it is first order for each reaction in each direction. If you start throwing in second orders, there's no guarantee that it's going to end up behaving like this. So it's just interesting for this specific reaction. So let's go back and answer the rest of the questions. So the next one is asking part B, when does the maximum concentration of our undesirable product occur? So let's run that again. We were kind of messing with that. So our undesirable is going to be right here, the blue one. So it happens at some time less than 1. So what we can do is we can say, let's go less than a minute. We can say, okay, our undesirable maximum concentration is going to be right here, roughly 0.03 minutes, which is what you get inside the text. However, you can do that by actually determining the derivative of the concentration profile, taking the derivative of the concentration and finding when it equals 0. And we can show you how to do that right now. Okay, so by using this function, we are able to determine what is the minimum value. So quick explanation is we are just storing a point here that is based off of this minimization function. So this is just taking the array that we created, giving all the data points, or it's just capturing the calculated values. This is just taking the absolute value, so it doesn't matter. We're just taking the smallest value that we possibly have, or I'm sorry, we're just taking the absolute values of all of the calculated data points, and then we're finding the minimum here. So the min is just saying that we are taking the minimum value of this absolute value of this stored array, which should be the closest value equal to 0. What this syntax is saying right here is that we are then ignoring the point. That's what the tilde right here means, is that we're just going to ignore what the actual calculated value is because we don't care. And the IDX means that we're going to display or capture the index of that minimum value. So what we're just saying is we're taking the index of it, which is the t. Since we're doing, we're plugging in it's going to capture the independent variable. So whether or not you're doing dy dx, it'll generate x. If you're doing dy dt, it'll generate t. If you're doing dy dz, it'll give out the z value. This is just say that we're getting the index value, which is another way to say we are getting the independent value. So all this is going to do right here is this is just all for generating a nice looking format right here. Which you can say this is just going to be what is exactly displayed. Everything going further is just letting you know that there's going to be, so this is just telling you that there's going to be a 3-digit decimal that's going to be coming into the display. And this is telling you that it's a new line character. It'll just take the cursor to the next line of printing, and all this is going to do is just retrieve it. So all this to say is that you can really cut it down and make it much simpler if you want to. So you can just do, so what you can do is, you don't care about all that, you can just say display the indice of the t value that was stored. You see that you get this value right here, same value. So that is how you go about figuring that problem out. The easy way is to just do the graphing and just figure out what the data point corresponds to there, or you can actually take the derivative, find the points, find the minimum, and figure out what the maximum and minimum is that way. So that was part B, asking when does the maximum concentration of U occur? What are the equilibrium concentrations of A, D, and U? So we can do that by just taking this to a very long period of time. We can call it 100, run it. And we can say that the equilibrium concentrations is, for this to be the y value, so it would be 0.82. This one would be 0.098, and then you can have here 0.082. Another thing that you can do is you can actually display what the final value is, so you can do that here. So by opening up what are we storing in the y is you can just scroll all the way down, and that'll be a way that you can get it as well. So a few ways that you can do it. You can just go into it and just grab the last value. You can also have it displaying the final value, but yeah, you guys can do that just fine. The next part of this problem says, what would the exit concentrations from the CSTR with a space-time residence time of 1 minute, 10 minutes, and 100 minutes be? So for that, we have to redesign the equations because we were doing it as functions of for a batch reactor. So for that, we have to go back to something else. Okay, so for part D, it's asking us, what would the exit concentrations be for a CSTR for given different residence times answered? So we want to do for a CSTR in terms of residence time. So let's start with what the design equation is in terms of flow rate. So we can say this is FA naught minus FA all over negative RA. So we know also that the flow rate of any species is going to be equal to the concentration of that species times the volumetric flow rate. Right? So if we plug that in, we get that the volume of each one of these species, or the initial flow rate, change to concentration of whatever that species is times the flow rate minus the concentration final of whatever species that is times flow rate over, for this problem, the V's, the flow rates, are not going to change. That has to do with the stoichiometry. So we have A going back and forth to only one D, and then we have A going back and forth to only one U. So no matter what is happening, nothing is changing as far as volume. So if it's in a gas form, if it's in a liquid form, you don't have to worry about it because volume remains the same. But for this one, we are going to say that technically this should be just V, but V is going to be equal to V naught because we're not experiencing any expansion coefficients. We're not getting any changes in volume due to stoichiometric effects. So we can just say that this is just going to be V naught, which means we can factor it out and say that V is equal to V naught times Ci naught minus Ci, or negative Ri. And this is going to end up becoming, if we divide it, we get that we have V over V naught, which is just equal to our residence time, which is equal to concentration initial minus our concentration final over our rate of reaction. Okay, so what that's going to then look like is it's going to translate for each one of the different types of products that we are, or different types of concentrations, which I will show here. Okay, so here are the equations for how the concentrations are going to change in a CSTR as a function of your residence time, as well as just your C of A. So this is where we then plug this into the MATLAB code. Okay, so when translating over to MATLAB, you get this, but let me just point something out real quick here. When running through the equations, I had put a negative for both, but there's only a negative for this first term right here. These other terms do not have a negative. So when using MATLAB, what you want to do is you are trying to solve these three equations simultaneously because they're all dependent on one another. So the first thing you have to do is write SYMS. What this is doing is it's creating these symbolic variables that we're calling CA, CD, and CU. Then what you're going to be doing next is just calling out the constants, which is just given in the problem statement. The next thing is you want to figure out, you want to define what your time is. And then given those, given the equations that were in the PDF, you know that you are just going to say, okay, equation 1 is going to be equal to our concentration of A, which is going to be, conditionally equal to, or these double equal signs, to the equation that is just from the design equation here. Then you're saying that equation number 2 is equal to our second design equation. Equation 3 is our third design equation, which is our undesirable product. And then the last thing that you're going to want to do is you're going to want to tell MATLAB to solve the series of equations. So you're going to solve your first equation, your second equation, and your third equation by varying the variables CA, the symbolic variables of CA, CD, and CU. So if there's a fourth equation that you had here, maybe there's another product or reactant, some other letter B or whatever, then you would just have an extra equation and then an extra term here. And then this is just simply for displaying the results. You're just doing a print. Again, this is just saying wording. So that way when you display the results, it gives it to you in a nice, neat little thing here. So let's run this at time equals 1. So if we run it as time equals 1, we're going to get the concentrations for a CSTR given a residence time of 1 minute. You get that the final concentrations of A is equal to this, concentration of D, concentration of U. That's going to be your outlet concentrations. This is just going to be using the fprint function, fprintf. So this is, you're just essentially telling this part right here, again, as I mentioned, was telling MATLAB that you are going to be, you want this to be said, and then the parentheses is going to be saying, again, that you have a 2 decimal place number coming out. So you can just pretty much copy this format, and then comma, what t value that you just inputted, which in our case was just 1. Next, you're going to just print out what the solved variable was. So it's a double, so it means you want something that's decimal place. It's not just a single number. You're displaying a double of the solved value of CA. So you're just saying, right here is CA is this, CD is that, CU is that. You can then change it for the time that it says. You want to do for 10, you can do 10. If you want to do for 100, you can just add an extra 0, and then you can keep going. So, of course, as residence time goes up, we expect the concentrations to change because you're giving it more time inside the reactor. So we notice that going from 100 to 1,000, like for example, our undesirable is not changing that much compared to going from 10 to 100. That's because we can give this as much time as we want, but then it kind of starts to become a batch. As we go quicker and don't give it enough time inside the CSTR, the values begin to decrease. So this whole problem was supposed to determine how you can use the batch reactor to figure out how it changes the concentrations over time. And once you have the kinetics based off of time from a batch reactor, you can then relate it here to residence time. How long is the average molecule or chemical going to be spending inside the reactor? So if you wanted a specific desirable concentration, you can do it for a batch. Then you can say if it's going to be about 10 minutes in the batch, it'll be this. Then we can run a CSTR. You can use it as a jumping off point to figure out what is the time for the CSTR. Okay, hope that helps. If you got any questions, please feel free to reach out. But going forward, definitely want to see that you are using some type of software where you are able to actually plot what it is that you're asked to plot. So I know that Polymath is free, but if it says to plot concentrations and conversions, then you're going to have to use a program that allows you to plot concentrations and conversions going forward. Okay, hope that helped. Have a good day.